Uno, uno, uno. Estamos probando la nueva consola de audio. Queremos ver si no hay eco. Rafa, ¿cómo lo escuchas ahí en los audífonos? Bueno, listo, Rafa. ¿Y está escuchándose bien? ¿Está escuchándose bien ahí en los audífonos? Y aquí también no hay retorno. Está sonando un poco mejor. Menos ruido blanco. Okay.
Yeah? Ready? Okay, so this second class for today is going to be a presentation. No more formulae on the blackboard, I promise. You must be sick of them. I'm certainly getting very tired of all this mathematics. So the topic of today is to see where we can use strong lensing as an application, as an actual tool in astronomy and in cosmology. And as you will see, there are various places where it's very powerful and very useful. So the obvious place to start is with mass measurements. Gravitational lensing is a phenomenon to do with masses bending light. And so if you can measure this light bending effect, then you can measure something about the mass of the lens is doing it. It's like having a piece of glass and playing around with it, looking at things and using it to figure out how strong the lens is that you have in your hand. It's really the same thing, but now with lenses up in the sky. And as we saw before, if you can identify a nice Einstein radius, so a single source that's imaged into an almost complete circle, then you know that you have, then you know what the average surface mass within this Einstein ring is. So if you can measure this ring here, then you know exactly that the average mass density within this ring is equal to the critical density. Kappa equals 1, which means the surface mass density equal to the critical density. And you see people have found a number, and there are many more than a number of lenses where you see a foreground galaxy. That's the yellow thing. These are typically large, massive elliptical galaxies, almost perfectly aligned with the background galaxy, which is often a much fainter blue thing, which then gets transformed into this beautiful, almost complete ring-like shape. And so these are some of the best anchor points that we have for measuring the total masses of galaxies. It's very difficult to measure the mass of a galaxy because all you see is the light, but here we get a good measurement of the total enclosed mass, and you see that's actually most of the light of this galaxy. And this is one of the ways that we know that galaxies are surrounded by a lot of extra matter that we don't see, masses tend to be a lot higher than what you would expect just from the stars that we see in these galaxies. And the other nice thing about mass measurements from lensing as compared to the other ways that people measure masses, which is typically looking at dynamics, looking at how fast stars move around inside galaxies and trying to figure out how hard they pull at each other that way, is that there's really no dependence on many of the uncertainties that you otherwise get. So you don't have to know anything about how the stars are moving around in this galaxy. There's no dynamical assumption that you have to make. You don't have to deproject anything. You get a very direct measurement of the total amount of mass enclosed within this. Yeah. This is to keep Jorge healthy. It's very good.
Entonces, la pregunta es si la expansión afecta el lenzamiento de alguna forma.
The expansion of the universe, you mean, or it affects things to the extent that the distances that we have in the critical density, remember this is scaled to the critical density, which has this dD and ds and dds, and those are affected by the curvature of the universe and the expansion. But it's only in there. So in a sense, all that matters is what this galaxy looked like at the time that these light rays flew past it, and that's exactly what we see, because that's the light that we get from this galaxy. Now, because these galaxy lenses are so powerful and so useful, people have spent a lot of time trying to find them. And there have been many, the first ones were basically found by accident, but now there are many systematic searches to try to get really huge samples, many thousands of these lenses to try to do large statistical studies. And there's a few ways in which you can try to find galaxy lenses in a way that's more or less unbiased. And the first thing you can do is you can simply look at all the galaxies which are most likely to be lenses. You look at the brightest elliptical galaxies, which we know are the most massive galaxies we know, and so those are the ones that are the most powerful lenses, and so they're the most effective at actually creating an Einstein ring, for example. And finding elliptical galaxies you do by looking at colors and magnitudes of galaxies. And then once you've looked at a whole sample of elliptical galaxies, you take pictures of them and you see which ones have some blue or arc-like structure, which would indicate a gravitational lens. Once you have that, you start to investigate them in more detail and see if it really is two sources, one behind the other, and whether lensing is the right explanation. That's a lot of work, because you have to take a lot of images, analyze the images, throw away a lot of things which look like lenses but weren't, so it's really not very easy. There's a very quick way to at least make some headway with it, which is to take spectra. The Sloan survey, for example, has taken spectra of...
I'm sorry for interrupting you, but is it an selection that most of the lens galaxies seems bluer than the lens, or there is I don't know, an astrophysical effect producing this kind of different colors?
It's astrophysical. It's because the source galaxies are usually intrinsically much fainter. I mean, the small galaxies are much more common than the large galaxies. And so if you have a lens and something is behind it, the chances are that it's going to be a small, faint galaxy. And those tend to be blue. So it's very unlikely that you get a big, mature elliptical galaxy behind another elliptical galaxy. So that's why there are some cases of red galaxies being lensed, but most of them are blue. So we can also look at spectra. For example, the Sloan survey has taken spectra of literally millions of galaxies, so we have a lot of galaxies with spectra. And the idea of those spectra is that you'd measure the redshift, but if you have a lens, then you actually have two galaxies, one behind the other, and so you will get two redshifts. You will get the redshift of the lens, but you will see that there are spectral lines which are in the wrong place, which are much more redshifted, as if there's another source right behind you. And so, for example, the galaxies in the previous slide, all these things were actually found. These are found, I think that's right. These are found in the SLAX project. The SLAX project is the Sloan lensing project, where they looked at all the spectra and they looked for spectra which looked like those of elliptical galaxies, but then with extra emission lines. And so, in a sense, here there is a selection effect because these were found as being emission line galaxies. So those really tend to be blue star-forming galaxies. So once you have a spectrum in which you have two redshifts, then you know at least that within the slit or within the fiber where you took the spectrum, there are two galaxies. And then the chances are that there is some lensing that's going to take place because they're nice and long. So that's how some of the best lenses have been found. And the other thing you can do always is if you have a sample of objects at cosmological distances, for example, bright quasars or bright supernovae or something like this. And almost always the brightest ones of those are things which have been lensed and which are brighter than they really should be. So if you have a sample of sources with a certain spread and brightness, and then you lens some of them, those will end up being even brighter. And so if you look for the brightest subset of any high redshift sample, almost always is going to be some lensing affecting their luminosity. And so here, just to prove that there's many more, this is one page of many of such lenses here. These are Hubble Space Telescope images. Maybe you can't see it from where you're sitting, but if you look later on the slides on the web, you can see that there's the main light in the middle. That's the lens. That's the elliptical galaxy. But then in all of these cases, you see some wisps. This is not a real one. But you see some distorted images, some wisps, which are the second galaxy in the picture, which has been lensed by the first one. You can try to enhance this by making a model for the lens galaxy and subtracting it off. And that's what you get here. So now the lens galaxy has been made to disappear, and now you can see much better that there are extra structures. There's this ring, for example. There's multiple images here, an arc with a counter image here. This looks a bit like the homework arcs in the center. This is a nice double image. Here's another one. All of these are cases where there is extra structure, which is this nice circular arc produced by things close to the Einstein.
In that second picture, yeah, if you go back to the other slide, you can see that that it's like a bit off axis.
Yeah.
Or isn't it? What kind of process makes the ring that it's a bit off axis?
So it's not actually a complete ring. It's two arcs.
Oh.
And it may be that that's to do with slight ellipticity in the lens. I mean, it can happen. You very rarely get an absolutely perfect circular ring. It could also be a little bit of structure of the source. The sources are not point objects, but are some extended source. Things like this. What you can do is you can compare these residuals with a model where they take the lens model that they've subtracted off and figure out how that might have lensed the background galaxy and compare that. And then you see really how amazingly good these models are. So this is a model, and this is the data after you subtract it down.
Maybe I didn't hear, but how do you remove the lens galaxy?
You fit the Vauquelin profile to it or something like this. You make the best fit the model you can and subtract it. So you assume that this looks like all the other elliptical galaxies that we know, and from that family you find the one that fits best. So it's not very sophisticated, but it works amazingly well. So this is again flipping between the data and the model, and you see that lots of really fine structures are completely. They agree extremely well. And so in these model fits, the only freedom that you have is once you've set the lens is to decide on where the source galaxy is and what the shape of the source galaxy is. And so all these things, each of these individual galaxies, we now can make a very good math model with because we have this exquisite lensing information. And even look, I find this one is really amazing.
And what about the lens potential? What does they assume for the lens potential in this case?
I'm not 100% sure, but I think it's also a fairly simple one. It's basically it might even be the singular isothermal lens with some ellipticity put in, and then some external shear sometimes. So a little bit of extra tidal effect from neighboring galaxies. So it's not that you're spending 100 parameters to fit 100 pixels or something. This is really very overdetermined. It's really very good. And so this is after a lot of hard work using Sloan spectra and space telescope images. Once we have satellites like WFIRST and Euclid, which will have the whole sky at space telescope resolution. Basically, there's going to be literally thousands and thousands of lenses. So this is going to turn into not something where one PhD spends his thesis modeling one of these systems. It's going to turn into somebody writing a computer program that can model 1,000. Okay, so lens masses are you can measure some aspects of the lens masses extremely well using lenses, particularly when you can identify the Einstein radius. You have a very well determined mass, but there's some things you cannot do. You cannot measure the radial mass profile very well because you really only have information about the lens at the location of the images. You have no idea what happened to light rays that pass somewhere else because we don't have images. And so the radial mass profile, the surface density as a function of position, is something you have to get from something else. You cannot really get that from the lensing itself very well. There's a few clues you can use from lensing. You can use the magnification, because if you have a lens, for example, where the images are asymmetric, if you have a lens galaxy here and you have one image close in and one image far away, then the bending angle here is very different from the bending angle here. Of course, it's going to be somewhere in between. And also the rate of change of the bending angle is different here and here, because the potential is not linear. And so that's going to give you different magnification matrices here, basically different distortion matrices. And so if you can measure the ratio of these brightnesses, that tells you something about the ratio of the distortion matrices, and that is extra information about the potential. So that helps a little bit to give you more information. If you can measure time delays, that tells you more as well. But really, mostly what you do is you can combine the lensing information that you have with other information about the galaxy. You can use dynamics in the central bright parts of the galaxy, for example, to measure the central mass density or to estimate that. And then you can compare that to the average that you've determined from lensing. That tells you something about the mass profile. Sometimes you're lucky and you actually are lensing separate sources with the same lens, which are two different registers. So you can have one. If you look at it side on, here's a lens. This is us. And here's one galaxy and here's another galaxy. Then this one galaxy will be lensed into a nice Einstein ring. And this other galaxy maybe is lensed into a second Einstein ring around it. And that means that you now have two different pieces of information. You know the average mass or the total mass within this Einstein ring from analyzing this lens here. And you also know the total mass within this Einstein ring from measuring this lens. So again, you know the enclosed mass between different radii. Again, that tells you something about the way the mass profile, the mass changes with radii. But these things are very rare, right? So lensing, the single lens is rare, so the double lens thing is square times as rare. But there are some examples. Yeah.
How can you measure mass, actually measure mass, if you don't know the distances?
You need the distances from the registers. So you need
Okay, so you need the Hubble's law.
and Hubble constant, and in fact the whole. So you need to understand. You need to know the background cosmology. So in fact, all these masses that you get will have a dependency on the Hubble constant, just like the nanometer masses also. So you still need to know the actual scale. And this is where time delays can help, which is what I will come to. So what I showed you before were cases where galaxies were lensing background galaxies. And that's quite common because galaxies are quite common. So if you look for something behind the lens, you're most likely to find the same galaxy. But there are some cases where bright quasars are being lensed. And those are actually very, very useful as well. Quasars are essentially points. So you can get very sharp information about the lensing potential. Whereas galaxies are fuzzy things, so they're more difficult to model. Also, quasars often emit in the radio. In the radio, we can use interferometry and measure extremely sharp images. You can do VLBI and go to milli-arc-second resolutions even. So you're sensitive to much smaller image separations than you are even with Hubble. And people have done surveys of radio quasars and looked at them at high resolution, and they find that about 1% of distant quasars is actually split, is actually length. So it's a rare phenomenon, but it's not a completely uncommon phenomenon. It happens quite a lot. There's a lot of quasars. And typically the separations are of the order of an arc-second. So here's a typical 4-image quasar. I told you that you always get an odd number of images, that you should get 1, 3, or 5, or 7 images. Here we see 4, and that's because the 5th image, which has to be in the middle, is the one that corresponds to the peak of the Fermat potential. That's extremely demagnified and is basically too faint to see. And that's almost always the case. Even though there should be 5, the central one is really.
Could you repeat that? I didn't understand that you said.
I said lensing, when there's no lensing, you have 1 image. And then every time you cross the caustic curve, then you generate 2 more images, or you annihilate 2 more images. So the amount of images you have is always odd, never even. You start with 1 and you always add or subtract 2. The pair that annihilates or 2. So this quasar should really have 5 images, not 4. And it does. It has 5 images. So the 5th image is the one that corresponds to the central peak of this Fermat potential. And there the gradients are very, very strong. The second derivatives are very strong, which means the magnification is very low. And so actually, there will be a 5th image of the quasar here, but it's so faint that you don't see it.
Also, you can deduce from the image that the symmetry, the axis of symmetry of the distribution is along this A to B because of the magnification. Is okay, or maybe in the direction from C to D. You can obtain this information from this.
I'm not so sure. It's not really completely symmetric, right? I mean, you could say there's a symmetry axis here as well. So it turns out there's actually a lot of ways of making 4 image configurations that look almost symmetric. So you really have to model these things in detail to be able to show. But what is clear is that this is not an axisymmetric lens. If you have a round lens, then you cannot make 4 images which do not lie on a straight line. so if you want to do this kind of survey, either you go through catalogs of radio quasars and look at them in high resolution, or you can try to target quasars that you select optically. So optically, quasars have very different colors from galaxies, and so if you have a large survey, again, like Sloan, where you have lots of different filters, there are techniques to pick out the sources that are probably quasars and not galaxies. And very often you find some color combination of bands in which the quasars are very blue, whereas the galaxies are very red. And so in the optical, then you have a very nice contrast also between the quasar light, which is going to be very blue, and the light from the galaxy, from the lens galaxy, which is very red. And in the radio, in fact, usually the lens galaxy is completely invisible, so you have a very clear view of the image positions of the quasar. And so again, there are hundreds of cases like this now known. Here's another example. This is a space telescope image of one of these radio-selected quasars. You see, this is an infrared filter, optical, near infrared, a bit further infrared. And you see that as you go to the redder, it actually pops up. Right? In the optical, the galaxy is basically invisible because it's very red. And you just see the blue quasar light. And then as you go to longer wavelengths, the galaxy is invisible. And this is important because it's an extra constraint on your lens model. If you know where the center of the lens is, that's an extra degree of freedom that you don't have to model. You know where to center your potential. And I think I have a few more examples.
Is there any effect of the wavelength in, okay, maybe a very subtle effect of the wavelength in the lens effect? I mean,
there shouldn't be. Lensing is completely achromatic.
Achromatic, okay. But you have an intergalactic medium. I don't know. I'm just wondering if you have maybe a different dispersion relationship. I don't know.
Okay. It's very hard to find something which has the same optical power as the gravitational lensing. So here's another one. So this was a project called the Castle Survey, where they did a lot of this imaging to get different things. This is an interesting one. This is a case where you just have two images here. But when you go to longer wavelengths, again, the lens galaxy shows up, and the lens galaxy in this case is not one of these elliptical, more or less round galaxies, but it's actually a more or less edge-on disk galaxy. You even see the dust laying here, going through the middle. So this is a case where you can measure the mass profile of the bulge of a disk galaxy from lensing very often. All right. And so these asymmetric lenses are actually very interesting because they give you this phenomenon of time delay. So let's talk a little bit about this. We talked about it before already yesterday, but if you have a multiple source, this is us, this is the source, these are the light paths, then you see just by eye that the length of the different light paths are different. This looks like a longer way to get to us than this. And this means that light that comes along here will arrive at a different time from light that comes along here. Now you have to add also this famous Shapiro delay in here. So when you go through a gravitational field, also your time slows down in a sense. And so it's not actually obvious by eye to say which is going to arrive first and which is going to arrive last. But nonetheless, there are differences in time delays, and that's what this Fermat potential expresses. That's what it calculates. If you can measure this time delay, so let me do my cool animation here. So the quasar emitted a flash, the flash starts to travel, and you see that by the time it gets to us, the two flashes arrive at different times. I'm so proud of this that I'm going to show you. And so if you can measure the time delay here, you effectively measure the distance between the distance in time between these two paths, between this path and this path. And that's the way of setting the length scale of this whole problem. So this is a diagram which is just in dimensionless units. It's just about shapes and angles and relative distances in which you don't know the Hubble constant. But if you can somehow measure the difference between these two light paths in actual seconds or in meters, then you have a way to really calibrate this whole diagram and set the scales properly and also deduce the Hubble constant. And in fact, one of the exercises, not in your homework, but one of the exercises in the quiz tomorrow is going to be to work through a calculation like this. Get the Hubble constant from a time delay quasar. So this is a simple case where you just have two images. Often you have
Again.
four, and then you have even more constraints because you can
Good.
compare the angles.
Again, which is the exercise that will be in the quiz tomorrow?
The quiz tomorrow.
Yes.
It's not in the homework.
No, it's not on the homework. But which is the problem? Is to calculate the distance from the time delay?
You will see, but something like that. You want to get a good grade. Yes, it's basically this. So you have a lens where you have to work out the geometry and then from the time delay work out all the distance. Okay, and so then if you were to monitor this quasar, then you would see two blips in the light curve, one after the other. And this again is a phenomenon that's not just theory, this has been observed. And I'll show you an example in a minute. So this is all the information you need to do this calculation. We've gone through this before. The Fermat potential, when you scale it with the distances, gives you this arrival time distance, and that's all you need to know. So here's an example. This is one of these 4-image quasars again. These are the light curves. So people were looking for this effect. Once you see that one of these quasars is variable, then you know you can try to make this measurement. And so they've been monitoring this quasar for hundreds of days in this case. This is almost a year. And you see image A, B, C, and D at lots of different times. They measure the fluxes of these images. And you see that they each fluctuate up and down, and they each look different. Sometimes image A is brighter, sometimes image B is brighter. But if you start to look for common features, then you see that you can actually slide these light curves on top of each other and make them coincide. Not so easy to see over here, but once you do the correlation and you slide them on top of each other, then you see that the combined light curve is actually very clear.
What is, on average, the order of magnitude of these time delays?
Days to months. So in a quad, some of these images are very close together, and also the time differences are very small. So these can be days. If you have a very asymmetric lens, then across images is going to be of the order of a month. So it's actually very nice. It's a very human time scale that you give. Like, fits within a PhD thesis. Yeah. And the reason it's so small is that I'm drawing these very exaggerated angles, but really the angles are very, very tiny. And so it's also quadratic, right? This distance and this distance is actually almost the same. The difference is only goes like the cosine, so it's a quadratic effect in the angle. So you'll see when you do the calculation tomorrow in the quiz that the numbers are very small. Typically 2 arc seconds. This is arc seconds in time. 1 arc second, 0 arc seconds, minus 1 arc second. Is that what you mean? Good question. Okay, so much for time delay. So that's so we've seen 2 applications now. We can measure masses of galaxies by the way they bend light very accurately, and with these time delays we can do geometry, and we can actually measure the size of the universe. We can try to determine the Hubble constant by analyzing these triangles. Now, of course, one limitation in all of this is that you have to understand your lens model. You have to make sure that you know what your lens looks like and how it's bending light. And one of the models seemed to fit very well. I showed you all these models in the beginning, which really explain the lensing configurations very nicely. But nonetheless, if you look at smaller scales, there are uncertainties. And for example, the way we think of galaxy formation now in the dark matter cosmology, when you do simulations to see how dark matter clumps starting from very smooth initial conditions into galaxies, you find that you make very big dark halos, but you also make a lot of small substars. This is a simulation of dark matter particles, and which has then been colored to make them visible, because otherwise it would be black, of course. And you see that you make a nice elliptical halo-like object in the middle, but lots and lots of clumps, lots and lots of satellites. So not a single smooth distribution like I've been working with and doing mathematics with the last few days. So is that an important effect for lensing? The fact that lenses probably are not completely smooth, how is that going to affect our results? And it turns out you can actually see this and you can try to measure this with lenses. And again, the best examples are the cases where you have a source very close to a critical curve, because that's where all the lensing effects are very strong and when you can measure things like that. So here is an example of one of these Einstein rings, or near Einstein rings. This is a source lensed into two images. It's an extended source, so you don't just get 2 points, but you also get a lot of extended structure around it. You can try to model this lens and work back to the source plane and see what the source looks like, and you end up with something like this. Looks like a fairly normal blobby little galaxy. Very magnified. Look at the scale. This is 0.05 to, this is, each of these 6 is 0.1 arc second. So really magnifying a lot from a 1 arc second across Einstein ring. So this is the data. Here is one of these models that you can put. It looks extremely similar. This is the same kind of code that was used in the slide I showed you earlier. And you can then look in detail at the difference. You can see what's the best model I can make by playing with the source geometry, playing with the lens model, and then you end up with some residuals, and the residuals are pretty good. On the whole, it looks like you're able to fit all the structure that you see in your data. But nonetheless, you can ask, can I tweak the lens model? Can I add some small scale structure to make the lens model even better, to make the model look even more like the data? And they do that by adding a kind of correction to the lensing potential, which corresponds to a correction to kappa, to the surface density, to convergence. And you see that they find here a very significant improvement in the accuracy of their reconstruction if they add a little clump here in the lens, a little piece of extra mass. Right? This is not light. This is a piece of extra mass in your lens, which somehow changes the way this galaxy is lensed near here, which makes the model look even more like the data than it already does. And so you can tweak these models and go through, and eventually you stop because you can decide whether something is statistically significant or not. But these people, this is a collaboration of colleagues of mine, these people claim that this, for example, is a very significant effect. Like you really improve your fit significantly. It's very hard to see because the data are so good, but you really improve your fit significantly by slightly tweaking the potential. Most of this is tough, some of this requires an extra step. And this is the kind of thing you would expect if you believe that dark halos indeed look like this, and not like the smooth ellipticals that I've been writing down in my form. So who knows? It may be a way. It seems to be that lensing is certainly sensitive to these clumps, and if we do this systematically, it may actually be a way to measure how often they occur compared to the simulations and learn something about dark matter, galaxies, halo formation. So very powerful, and it relies again on this very high fidelity, very accurate images that you're able to make at these lengths.
Kun,
Yeah.
since we are talking about this second order effect, I was wondering if you can measure some sort of self-lensing. I mean, for example, if you have a huge object whose image is distorted by itself, is it possible by itself? Okay, the halo mass, the mass in the halo of this object can lens another part of the galaxy or something. This is a fourth order effect.
Yeah, I think it's not necessarily fourth order, but it's just very small because the critical density depends on this distance ratio. And if the distance between the deflector and the source is very small, which is what you're saying, right? The lens is inside the galaxy, they're very close to the galaxy. Then all the lensing angles become really tiny. So you would need a huge amount of mass to make this a measurable effect. So I don't think it's, I mean, you really are dealing with cases where you have a very distant source and a lens almost halfway in between, which is what you need to get the most efficient.
Or maybe with the with this disk around black holes in the center of galaxies, for example, you can measure this kind of self-lensing. Okay, a correction disk around that.
But then you also have other effects which are very important, like gravitational redshift and frame dragging and all this stuff. So then you really are no longer in the weak tooth limit. So This, in a sense, all this is still very, very weak deflections. It's just happening in a case close to the critical curve, which is why it magnifies all these. Another way to look for substructure is not to look for residuals in these models, but to go back to these 4-image quasars. In fact, here we have this is the case. I'm not sure whether this is the lens now or whether this is actually a detection of the 5th image in this quasar. What's done here is people at Caltech or in California are using keck with a new adaptive optics camera in which you can make really effective, really sharp images, almost as sharp, in fact, as the radio images that you get. And so what they've done here is they've imaged this multiply image quasar. You see the multiple images, of course. But you also see, because you can see such sharp, fine substructure, you begin to see extra little galaxies in the field, which are probably associated, or at least perturbing, the lens that we have here. And so normally you would model a quark like this with a very simple elliptical isothermal plus some shear and not much else. But now if you look at the lens, then it turns out that you have to add an extra point mass or very compact optic. That's going to affect the lensing potential or your Fermat potential, and it may actually change not so much where the images fall, but what the gradient of the potentials of these images and therefore how bright they are relative to that. And this is a phenomenon called millilensing, and it's actually an interesting case. The configuration like this, you can show that this image B should on average be about as bright as the sum of images A and C, simply by how the second derivative of the potential works in a smooth situation. And you see that's definitely not the case. If anything, B is fainter even than C. So this source should be brighter, and it should be as bright as these two sources combined. And that means something here is changing the local slope of the lensing potential without affecting the overall configuration, without affecting the large-scale structure of the lens. And that you can do by putting a little blob of extra mass very close to this image B, and therefore you basically don't change A or C, but you change B. So, and you know, by looking for fine substructure, maybe it's actual little galaxies that you can see, maybe it's dark matter clumps that you cannot see. But there is a puzzle here in many of these multiple image quasars that the flux ratios do not actually match what you would expect from the smoothness. And that's a phenomenon called millilensing. It's in between the microlensing that we will talk about tomorrow, which is due to individual stars, and the macro lensing, which is what defines the overall image configuration here. So it's structures in the lens at a scale much smaller than the overall lens, but big enough to affect things like the relative sizes of the
Could you recall us what this F means? What is this quantity, F? Please recall me.
F here?
Yes.
This is the flux, so the brightness of the difference.
Flux.
So we haven't talked about this before, and this is something I have to skip. If you have a situation where images are merging, the two merging images are usually close to the same brightness because they kind of cancel each other out. And so in this configuration where there are three images together, then you can have these approximate relations. And here's another beautiful example. This is again a case where you have a very long arc of a galaxy. Here's the counter image. You see the lens very clearly in the middle. There's a few extra blobs here. But this galaxy G4, so G1, G2, G3, and G4 are all galaxies in the lens. This lens is a group with one massive galaxy and a few satellites. And this galaxy G4 happens to sit right in front of the image of this giant arc. And so you see that this little galaxy, just like in the movie I showed you earlier today, this little galaxy is locally perturbing the images and actually pushing them away from each other. And this is a fantastic way of measuring all kinds of properties of the potential due to this galaxy. Very active. Now here you see that the arc is disturbed and you see that there's a galaxy there, but imagine that you had another disturbance like this where you didn't see a galaxy. That would be a very nice proof that there is some dark blob there. And if you never see dark blobs like this, that also would be a very interesting indication because, as I said, cold dark matter theory expect these blobs to be around in the lens. And so the best way to do this in the end is going to be with very high resolution radio images. So the SKA, when it finally gets built, is going to have a resolution, milliarc seconds or of that sort of order. And so here's a simulation of what one of these lens galaxies might look like. And so you get these beautiful, very long, very thin features in a smooth model. As soon as you start perturbing this with blobs, with mass concentrations, you would start to see easy holes in this. So these will be fantastic probes of the smoothness of dark matter potential from lensing. But we have to wait for SKA to be able to do this on a large scale. So that's the third application, looking at substructure of potentials in lenses. Sure.
Sorry. So there is an alternative to dark matter called MOND, right? So how this theory predicts this same phenomena, and it's as good as dark matter model?
So MOND will not be able to predict small substructures because there is no dark matter to have substructure in. But what MOND still at the moment lacks is a predictive theory for lensing as a whole. So MOND is very good at predicting dynamics of galaxies, how stars move around in galaxies, rotation curves, this kind of thing. But it's not actually, there is no prediction for how light behaves due to MOND. One simple expectation might have been to say there is no, when you look at light bending in MOND, then it doesn't feel any dark matter, so all the bending angles are much, much smaller. So it's not actually clear. And there are other alternative theories of gravity in which there is a very clear prediction for what the lensing does as well. Typically those are not theories that try to circumvent the dark matter problem, but they simply try to fix things like the cosmological constant or quantum aspects of gravity and things like that. But MOND doesn't have a clear prediction for lensing, unfortunately. Okay, so fourth application is the gravitational telescope. I talked about this briefly yesterday. This is the idea that you have this big lens in the sky, you combine it with your big telescope on Earth, and you get a super telescope, a cosmological telescope, which we call the gravitational telescope, with which you can see much fainter galaxies in much more detail than you can if there were no gravitational lens in there. So we can do a simple calculation, for example, using the singular isothermal sphere. So in the singular isothermal sphere, here's our Einstein radius in dimensional units. You can show that both the convergence and the shear are equal to theta e over 2 theta. So at the Einstein radius, both kappa and gamma are equal to 1/2 for a singular isothermal sphere. Once you know kappa and gamma, you can work out the determinant of the distortion matrix, which is this 1 minus kappa squared minus gamma squared, and that gives you the magnification. That tells you how much bigger the source is, how much bigger the image is than the source. What the determinant tells you. It tells you how the area changes of a small area element. And so you can plug in kappa and gamma in this formula, and this is what you get. So this magnification at the Einstein radius is infinite. That's what you expect. It's a critical curve. So you're stretching a small image into a ring all the way around. So, but at other places, the magnification can be large, but nevertheless, it's finite. And so, for example, at a radius of twice the Einstein radius, or at a radius of 2/3 of the Einstein radius, the magnification is 2. And in between, it's going to be larger than 2. So if this is the Einstein radius here, and this is, then, for example, between 2/3 the Einstein radius and twice the Einstein radius, here in this area, the magnification is at least 2. So all the sources that you see here, all the images that you see here, rather, are sources that you see magnified at least a factor of 2. If you go even closer to the critical curve, you can do the same calculation. You can ask, for example, how close you have to go to magnification of 10, and you find you have to go between 10/11 and 10/9 of the Einstein radius. So a very thin ring around the Einstein radius. And of course, the closer you get, the larger the magnification, until on the Einstein ring itself, the magnification is infinite. And so you can also play games like work out what the area is, which is magnified by at least a certain amount, and you get this kind of thing. So the higher magnification you ask for, the smaller the area available for you to look. It's kind of surprising. It's not really surprising, but there's no free lunch. So that means that if you look at these areas close to the critical curve, you see background galaxies very highly magnified. But you're seeing also a part of the distant sky very, very demagnified. You're only seeing a very, very tiny part of the universe that's magnified into this area. And so when you use gravitational telescopes as a kind of survey instrument, it actually has pros and cons. Because the sources that you do see are magnified by this factor m. And so it means you see objects that you otherwise simply would not be able to see at all. But the downside is that you're actually also magnifying all the sky around it. So you're looking effectively at a smaller piece of the universe with your strong magnifying glass. And so depending on the luminosity function of your sources, you will actually see more sources or less sources when you point a highly magnifying gravitational telescope at them. So if you have here the luminosity function, it goes in good astronomy fashion from bright on the left to faint on the right. And this is the number of sources above a certain brightness. Then what you find is two competing effects. That on the one hand, the magnification makes all the sources brighter, so it pushes it in this direction, in this direction towards bright. That's the flux boost that you get. But also it makes the sources rarer because it's spreading them out over a larger area of the sky. And so it's decreasing the density that you get. And so depending on the slope of your luminosity function, here you will either get fewer sources due to lensing. That's typically at the faint end where the luminosity function is fairly flat. But at the bright end where the luminosity function is very steep, you will certainly generate more and more bright sources. So in fact, you can use this as a way of measuring the magnification by comparing the luminosity function in lens areas to the luminosity function in the rest of the sky. So this is called magnification bias. So faint galaxies actually disappear. They stay faint, but you simply lose the area in which they come. And brighter galaxies, which were not really there because they're extremely rare, are created by the extra magnification.
Can you explain me again, how do you measure the magnification using this luminosity function?
If you know the luminosity function on average of the whole sky.
Okay, luminosity function is yes, the number of sources at a given
brighter than a given magnitude per unit area. Per unit area of sky.
So, yes.
Right? Galaxies, galaxies brighter than a certain flux per square degree. So that's this top curve, this one here. Now if you go to clusters of galaxies where you know there's magnification, then you expect that this curve will extend in this kind of diagonal direction. So you can try to measure the luminosity function again in these areas where you think there is lensing.
Just in this area?
Just in these areas. And you can compare the two.
Okay.
And the amount by which this luminosity function has moved along this diagonal, that tells you how much the magnification is in that area.
Okay, but the point is the magnification will be different according to the point inside the cluster.
Yes, so you have to be very careful. You have to do
this mission
is conceptual. If you have, supposing you have a piece of sky with a magnification m and a piece of sky with no magnification.
Okay. So actually, you will have not a line, but you have a scatter. Yes.
Yeah.
Okay.
You have to parameterize it somehow and put the parameter. So here's a beautiful example of a gravitational telescope. This is one of the first ones that was discovered. This is a very massive cluster called 0024. And I think I showed you this picture yesterday. And there's this little ring-shaped galaxy that sits almost directly behind the middle. And it ends up being lensed by the complicated, messy potential of this cluster of galaxies into a total, I think, of 7 images. And the 4 brightest ones, A, B, C, and D, are shown here when you reconstruct them back to the source plane when you have a good lens model. And so you can combine all the information and get a really very good map of of this intrinsic galaxy at a much, much smaller resolution than a microscope. So not only do you see galaxies which are much fainter than you would be able to see, but you also see much finer details because of the magnification you utilize. And you can take advantage of the fact that different images are stretched in different directions so that when you combine all these things, in some cases the x direction will be magnified, in other cases the y direction will be magnified. So combining all this actually gives you a lot of information in all different directions. See, this galaxy was sheared in this direction, this galaxy was sheared in this direction. So this image and the combination kind of gives you isotopic information. And so I actually was involved in an experiment where we on purpose tried to use gravitational telescopes to try to find very distant high redshift faint galaxies. And so this is how you do this. You start with a model for your lens, so you have a cluster that you think you understand by looking at the lensing patterns that you have already, by looking at the distribution of galaxies in it. You calculate the magnification pattern. So this is, for example, a theoretical case with an elliptical isothermal. So you have the critical curves here. These white areas are the cases where the magnification is very, very high. The red is kind of the average magnification of 1, and the blue is where the magnification is actually less than 1. So this is useless. Things which you normally would be able to see, you can no longer see here. They're demagnified. But it doesn't matter. This is also where all the cluster galaxies are. So this is actually not a very useful part of this guide to work with. But the point is you try to identify where these very high magnification regions are, and you search them very carefully either with spectra or with Hubble Space Telescope images or whatever. And then you try to match up multiple image pairs and try to do this reconstruction like I showed you before. And there's lots of different ways of trying to match image pairs. You can use the colors, the morphology, predictions from your lens model. So this is quite a puzzle usually. And this is one of the first that showed up at a very high redshift. This is a redshift of almost 5, which was big news when it happened in 1997. This is a lady colleague of mine, actually, Marijn Frank, who discovered this. So this is a cluster of redshift of about 0.3. This is one of the first clusters that was really studied in detail with the space telescope over a large area, so not just in the center, but also the outskirts. And what they found was this very red thing here, which is enhanced here. A very long, strange thing. It really doesn't look like any galaxy that we know. And in fact, it turns out to be a lens image of a perfectly normal faint galaxy sitting behind the cluster. And in fact, if you look very carefully, there's a counter image somewhere there. This, if you switch off the lights, you might be able to see. So there's a little red blob which has exactly the same colors as this thing, and if you do the lens model, actually looks exactly the same. And so the reconstruction of this thing using both this image and that image shows that it's a little blobby emission line object at redshift. Basically, all you see is the Lyman alpha line in the sky. So this is a clear case where we're using this cluster in the sky as a piece of tool, to see things which otherwise we would not be able to see at all. This one and this one. I think first you do this with imaging. You try to model your cluster. I mean, there's other arcs in here which give you an idea of the lens model. And then you try to see, have an image here, where would there be other images? You can actually, right, you use your lens equation to trace this image back to a source plane, and then from that source you try to see other images. And then I guess they found that this would be a good place to look. But also kind of amorphous. You see it only in one band. You just see it in the red band in which the Lyman alpha line appears. So this kind of amorphous source is also very strange to begin with. I think there was some good luck involved as well. I should be careful what I say because the camera went. Here's a case in which I was involved myself. This was worked together with Richard Ellis, who is coming here soon.
Yes.
So we collaborated. This was in 2001. This is much, much fainter. So this is two little counter images. The critical curve of this cluster here runs right through here. So you expect double images either side of the critical curve. And we found this really tiny blob, which seemed to be in the right place. And when we took a spectrum of them, they turned out to be, I'll show you the spectrum. When we took a spectrum of them, they turned out to be absolutely identical Lyman alpha. So again, this is a spectrum where you just have one line, which presumably is Lyman alpha. So that's the only line that puts it at the redshift where the lensing would be efficient to make this double image. And so this was now discovered. This was the redshift 5.5. Very, very faint. So let me show you how we found this. We started off again one of these projects where you pick the best clusters that you can to look at the critical curve. So this cluster clearly is a very strong lensing cluster. There's lots of arcs everywhere. So it's a lot of surface mass density, a lot of strong lensing going on. And if you're targeting a particular redshift, you can work out what the critical density is, and therefore what the critical curves are, and that's what this line here is. This is the critical curve for redshift 5, I guess. I'm not sure exactly. And this dashed line is the critical curve that you get for a source at a lower redshift. And those critical curves will be different because the scaling of your critical mass density is different for your distortion matrix also changes with it. So we knew that this was an interesting part of the sky to look at, that this is where magnified sources would appear. And so with Keck, we did lots of spectroscopy. We basically placed long slits one after the other and took a long spectrum to see if there was anything in there, something very faint. And that's
how could you determine the critical lines, because you don't have a model?
So the model in this case consists of putting a mass on every galaxy that you see in the cluster, and also putting an overall halo for the cluster as a whole, with a few parameters like a mass, a core radius, and an elasticity, and fitting that to all the lensing features that you already have in this cluster. Right? We do know a lot about this cluster because there is a lot of other strong lensing going on from lower redshift sources. And once you have this, then you know the mass distribution in the lens, and you can ask, okay, how would this lens change further in the background? But it's kind of an iterative process. You start with the simplest lens model that you can. You try to see if that explains some of the multiple image sources that you find. And you start to tweak the model, add a few extra parameters until it gets more and more complex, but also more and more accurate. And so this is where in this area here, we found this pair of very red things which only showed up in one band, and that's those Lyman alpha emitters that we discovered here. And here, this is maybe the most famous strong lens. I think it's one of the first that people started to study. This was the first giant arc that people recognized here. This is a single small background galaxy which is actually multiply imaged, and the images are just merging here. There's other counter images of the same source somewhere else. I forget where now. And all these other things here, all these other things are pairs of our other multiply image sources. So this 8.2, for example, corresponds to 8.3, and there should be an 8.1 somewhere as well, 8.1. So these are 3 images of the same source. And there's source number 7, which is up to 5 images. There's source 9, there's source 4, etc. So lots of constraints of multiply image sources that you identify as being the same because they have the same color and the same morphology. And all that can be used to constrain the total length space. If you then add masses on all the galaxies in this cluster, and you see there are many, then you end up with these very complicated, very critical, very wiggly, very involved critical curves. So in a sense, this is the substructure that we see, except here all the substructures, galaxies are not dark matter. Once you've calibrated this cluster at a redshift, in this case 1.2, then you can do the same. You can use exactly the same lens model and work out where the critical curve will be for redshift 6. And that tells you that if you're looking for highly magnified redshift 6 galaxies, you should look on the sky somewhere near this red curve. So that's how you build up the knowledge using these gravitational telescopes. And now Space Telescope is targeting about a dozen clusters with very deep imaging to look at even larger radii where the critical curves for even larger redshift stars to try to find the faintest, earliest galaxies that you possibly can using Space Telescope. So
this is the way as most people discover these very far away galaxies, these galaxies with redshift 7 and redshift 8.
Many of them are lensed and so are behind clusters.
Okay, so gravitational lensing could make you very famous.
It has made a lot of people very famous. Ask Richard Ellis. And so this is a zoom in on this giant arc that was at the bottom of the previous picture. And you see that within this first galaxy, you can actually identify lots of individual blobs, and they all match up. So down here, can we switch off the lights for a second? So this is a reconstruction of the galaxy that's lensed here into what looks like a perfectly normal edge-on spiral galaxy. And all this funny structure is all because of the distortions that you're getting as a result of this lensing close to a critical curve. And here you see the caustics, or various caustics at different redshifts. And so if you study this, then you can see why some parts of this galaxy are imaged 5 times, why some are imaged 3 times, etc. So you can really completely reconstruct all this complicated structure as being due to the blobs in this edge-on spiral galaxy at a redshift of whatever it is, 1 or something. And these are different parts of the same galaxy, which are only imaged partially because they fall on top of one of these. Okay, so that's certainly a subject that lots of people have been having lots of fun with in terms of trying to analyze these. You can think of these things as puzzles in the sky. You have a cluster with lots of multiply image things, and you have to try to pair the images together and reconstruct what the lens has been doing. Okay, so that's it for today, I think.
I have a final question.
Yeah.
Question number 100. And is, okay, could you recall us the difference between critical curve and this caustic?
They're actually the same thing, except that the critical curve is in the image plane,
Okay.
and the caustic is in the source plane.
Okay. So this is the lensed image of this galaxy.
This is unlensed,
Yes.
and this is lensed.
Okay.
So this is the image plane, and this is the source plane. And these critical curves here have been transferred also to the source plane, which is where they give you these kind of stuff.
Okay.
And the more substructure you have in your lens, the more of these complicated stuff you generate. Because in a sense, you're really folding the wavefront in more and more complicated ways. Any other questions from anybody else?
I'm just trying to encourage you to ask even a stupid question.
No, it's very good.
Stupid questions normally are good questions.
Exactly.
Earlier you said that this lensing was achromatic, but does it in any way change the spectrum of the source?
No.
Doesn't shift it or anything.
I mean, you have gravitational redshift, which will shift everything in the same direction. That's kind of the equivalent of lensing, but done along the line of sight instead of across the line of sight. So that's really the only thing. Apart from all wavelengths are bent in exactly the same way. All photons feel exactly the same gravitational field and fall in exactly the same way. So that's actually one of the main ways of checking whether something is lensing or not, whether it is achromatic. Any other? You're not seriously going to ask me to answer the test question? You can start them now, and then if things are not clear, you can ask me now. It is very hot today, though. Is that fast or slow? Am I too fast? You should slow me down then. Okay.
I'm getting old. Okay.
And mine was on while I was not doing it.
Ok. Muy bien. Entonces, si no hay más preguntas, traigan mañana también ventilador personal porque... Ah, sí. Recuerden que las preguntas también se pueden hacer en español. No sé si habrán notado que Kun entiende español, porque su esposa es española.
Que si las presentaciones van a estar publicadas en la página.
Las presentaciones, los ejercicios, los libros, el link al video, todo está ya en la página. Incluso los videos que nos mostró en la clase de la UNA también está disponible ya en la página. Otra vez mañana yo voy a estar toda la mañana. Kun seguramente va a llegar por ahí a las 9:30 en mi oficina, los dos, por si quieren ir a conversar, a hablar, a preguntar, lo que sea. Es una buena idea ir a preguntar y hablar sobre las presentaciones y los ejercicios. Entonces allá estaremos disponibles para los que puedan ir. Obviamente algunos tienen clase, otros no. Ya hablé con los profesores Esteban y Juan Carlos para que algo de las actividades del curso las incluyan como evaluación de los cursos que están viendo los estudiantes de astronomía. Esto para que pongan más las pilas. Bueno, muy bien.
If you have more time and you feel like it tomorrow to prepare for the subject of tomorrow, which is going to be microlensing, the book on microlensing that's on the web, if you read sections 1 and 3, that's the material I'm going to try to cover. And then you can also read 2 and 4, which are for general interest if you want, but probably you won't have time. But it will help if you already familiarize yourself with sections 1 and 3. They're not very long.
Tomorrow's session will be very important for those planning to work on exoplanets and things like that, because this is a very important technique for us. So, okay.